equation satisfy the continuity equation. So in any time-dependent problem, if I write this in a more familiar form, the flux of current has to be equal to the rate of change of the charge enclosed and enclosed surface S. Okay. So let's look at an example, the paradox that we encounter when we talk about this on Monday. So let's look at the discharge of a capacitor. And for the purpose of this problem, I can make this line. Resistor R, capacitor C. So at time equal to 0, we have plus Q naught here, minus Q naught. Okay, so at time equal to 0, you here. At time equal to 0, you close the switch, right? So current is okay. And you remember from chapter 4, right? What happened here? Discharge is such that if you solve the differential equation with the Kirchhoff law, you find that Q is equal to Q naught to the minus T over RC, right? And then current I, as a function of time, is minus dQ T, right? Minus because of the direction of the current defined. And this will give you, if you did this correctly, also by the way, see just for convenience, Q naught is equal to C Q naught, right? This is the voltage across the capacitor. So this is going to become D naught over R e to minus T over RC. Okay? And for completion, the function of time is Q naught over e to minus T over RC. Okay? So what happened here? If I look at during the time goes to 0, right? During the time of the discharge, if I look at an Amperian loop here, or even here, or wherever, right? Amperian loop. Okay. Far away from the discharge, far away from the capacitor. Then Ampere's law tells you that a closed loop line integral of PDL has to be equal to mu naught I equals, right? So just what I is function of time. Okay? And so it's just usual consideration of symmetry, whatnot, and you'll find that V, which is in the tangential direction, 2 pi R is equal to mu naught times I, and then V, as usual, see the stick now. So let's look at what happened inside the capacitor itself. So what do you think? Inside the capacitor, because there is a plus Q here and minus Q, right? There is an electric field. And the electric field is given by sigma over epsilon naught. And sigma is just Q divided by the area. Let's consider the area. Let's consider a capacitor to be a disk, right? Two disks like that. Okay, of radius B, say. Okay, I'm just drawing in a perspective. Sigma over pi squared. Okay, so the electric field then is Q over epsilon naught pi. Now, as you discharge this capacitor, right? Q will depend on time, right? So there's a time dependence on the electric field. Let's calculate that. E then is just equal to 1 over epsilon naught pi squared times Q dot. Right? But Q dot is no more than just minus. By the way, the electric field here is in the x direction, of course. It's in the minus x direction. Right? So Q dot is just minus I, right? So this becomes 1 over epsilon naught by b squared I, function of time, right? But since E is in the minus x, there's another minus sign, so this is in the plus x direction.
I'm wondering why you made this, and so why is it pi?
Just for
convenience?
ease of discussion for convenience,
Okay.
yeah. And also I'm ignoring, as usual, you can see the situation. I'm not drawing it properly, right? I mean, this distance here S, and there's an area here A, right? Usual thing, the square root of A is much, much larger than S, right? So I can ignore fringe effect. So now that there is a, you know that inside the capacitor there is a rate of change of electric field. The electric field changes with respect to time, right? So you have a displacement current, right? Because you have displacement current, then the curl of B is not zero. Okay. So let's look at that. So if I look at if I this here, right, I'm blowing it up. So actually, if I draw an Hungarian loop, right, of radius r, okay, then from the Ampere's law, the curl of B is equal to mu naught J, in this case J is 0, right, plus mu naught epsilon naught d dt, right? This will give you a line integral of BDL is equal to mu naught epsilon naught the flux of d dt over the surface, right? Over this surface. Okay. So same usual consideration here. We have cylindrical symmetry, right? So the B field here is the same throughout the circumference of the Amperian loop times 2 pi r, right? Because this has a radius, I think you can see this as a radius r. It is equal to mu naught epsilon naught. What is d dt? d dt is 1 over epsilon naught pi b squared, right? Times I as a function of time, right? And it's constant, right? As usual. In a capacitor, everything is, if you know, difference of fact, it is constant. The rate of change is constant. So this is just the area, right? And this area is just pi r squared. Okay. So if I collect all the term, then I have the inside the capacitor. This is inside the capacitor. Okay. Is equal to the epsilon naught cancel, mu naught over 2 pi r, I as a function of time, right? R squared over b squared. You can massage it however you want, but as you see, this b, right, as a function of r, is actually b, right? There's a factor of r. Terms there here that cancel one factor of r squared here, right? Okay. So same thing here, ignoring the fringe effect outside, right? It will be dropped as 1 over r. Okay. I'm not solving that part. I'm just solving inside the capacitor.
Is that part S, or
Sorry.
is it S or S half? Or,
S.
like when's the distance until
Or
it?
these R.
Yeah, but I mean, when's the distance until it reaches outside the capacitor?
This is outside the capacitor. So if I look at the field outside of the capacitor, this is the capacitor. Oops. Right.
Yeah.
So if as I go along the radially, right, from the center, the field increases linearly, right. But once I reach the edge, right, if I can ignore the fringe effect, right, then basically it should analytically continue to what happened here. Over here, you see the field goes down as 1 over R, right?
Yeah.
So it should be the same over here too,
Oh, okay.
right?
Yeah. I was thinking electric field. Okay. Yeah.
Okay.
So when you were calculating the field as some other ring,
Yes,
you didn't
yes.
have to take into account dEdt. That was only when you
Yes. Well, it depends on what surface you use.
Oh.
Yes. Here I'm using this example to actually calculate the P field inside.
Oh.
Yes. Okay. Right. I mean, you can choose the most appropriate surface for your calculation, right? Say if I want to calculate the Ampere's law over here, right? I could also use this surface if I want, right? And you can make some approximation, and you also again ignore the fringe effect. Here the fringe effect is even bigger, right? Because as you see, there is an electric field like that, right? The capacitor is finite, so there is a field. There is fringes everywhere, right? So you have to take into account all the surface integral on this balloon slide of the surface, right? Not just the flat part, right? So it's a lot more difficult to calculate.
Wait. So what is making it increase inside, like as it moves outward, and then it drops? But I mean.
What makes
Because it's moving out. It's moving linearly.
Oh,
right?
yes,
So-
the B field increases because of the flux of displacement current. You have more displacement current in that, just like in the same idea, right? If we call this example that we had, right, it's very similar to this problem. If I have a cylinder, right, and a current density J is just I over I P squared, say, right? It's just a speed, right? Then the magnetic field, if I want to calculate the P field inside, right? This also goes linearly as well. The P field here for this problem, right, which is a constant current density, the P field is also tangential, it's linear, and then it drops as 1 over R. Right. Same thing here. Think of the, Maxwell had the equation correct, right? Think of this term here, epsilon naught dEdt, as a displacement current, as a different kind of current, right? Not a real charge current. I mean, it's an old archaic term, right? Nobody call it displacement current nowadays except in textbooks. So, but I guess it's still called that. But that's the idea, right? Same thing in the capacitor. In that capacitor, right? Because there's an electric field that's constant, right, over the cylinder, right, and it's changing in time, right? That gives you a constant current throughout the capacitor, and that leads to the field. That's actually the This is confusing. This is actually very straightforward. If you just think of this term here, right, just an analog as a current, right? Then everything is straightforward, right? Just think of this as a different kind of current, right? And then just blindly apply Ampere's law. Okay. So now that we iron out all the inconsistency, because of time dependence of our electromagnetic problem, let's look at the consequences of this for Maxwell equation, the completed Maxwell equation that we have. Let's write that down. What have we done so far? This is you're in the process of making that t-shirt, right? T-shirt. How do you write this usually? With an apostrophe S or not? The fourth equation.
We actually can I ask you a question about
Yes.
these things? So, when you're just calculating around a loop with a surface that's like not have a capacitor,
Yes.
why is it that you don't have a DET term? Because like, isn't there an electric field that's changing inside the wire and that's like passing through the surface, right?
Yeah, well, most of the DET is over here, right? But it's true, yeah, there's the fringe effect, right? But I'm ignoring the fringe effect right now.
Where I just meant like
But,
in terms of, because like the current's increasing, right? So isn't there isn't there an electric field in the wire that's causing the current to move in the first place? And that's like a DET, isn't it?
Yeah, I mean, you have that, but you will find it. There is a DET in here, right, confined to the wire, right? There is a current, and then this is ohmic, and this is sigma E, right? So in theory, yes, there is an electric field in here, right? I mean, it's a bit more complicated, but that terms, you saying that if I just look at this, right, and I'm going to look like that, right? I mean, it's a good question. If I'm going to look like this, right? DDL, not J, why don't I add JD, right? That's your question, right? But this is a lot smaller. Way smaller, especially if you don't have anything changing at high frequency. This is what I mentioned briefly in the discussion yesterday. I don't want to visit that in this lecture. It's a bit more complicated. But part of the reason that Faraday did not discover this, right? This I mentioned exactly what I said yesterday. This is what Ampere's found, right? And Faraday did the most extensive experiment on the uranium. Right? And he found Faraday's law, right? And then of course he did a lot of experiment with Ampere's law. He never found this, right? Because this term is completely swamped by that term. The J term is a lot bigger than the JE term. That's the reason. Right? So I think the same explanation also answered your question. But if you have, you're just looking at the discharge of a capacitor, right? Suppose you have a time-dependent problem. Suppose the capacitor is triple, right? So you have something that's changing with the cosine omega t, and omega is actually very large, right? Then you have to start to program like this, because you have a radiation problem. In that case, you have a completely different volume. And then this is what we want to do next. Good question, giving me honest. So Maxwell equation, and now you should all be able to write this into your sleep. Right? I'm writing only the differential form from now on, because we're moving on. So which one is the Ampere's law? This is the Ampere's law, right? And this is the Faraday's law. Right? Mu naught J plus mu naught epsilon naught. Okay? Now, in free space, space, suppose I look at the region of an area or a volume where rho is equal to 0 everywhere, okay, and J is equal to 0 everywhere. then what do I have? I have, look at the Maxwell equation again. Divergence of E is 0. Divergence of E is 0. Curl of B, which one did I write first? Curl of E. Curl of E is equal to minus d. No modification there. But curl of B is just equal to, by the way, if you recall from chapter 5, right? From chapter 5, this is actually equal to 1 over c squared. Right? C is equal to 1 over square root of mu naught epsilon naught. So this becomes 1 over c squared dE. Okay? This is in free space. Okay? Let's see where is the ordering of things. Okay? Here. Now, if I take a curl of E of equation number 3, number 4, curl of equation number 3, and I have a curl of E. Okay. And that has to be equal to minus curl of the okay. Let me change the order of the differentiation. You can always do that. Okay. Blindly, you can just do that. This becomes then minus t curl. Okay. But what is curl of B? Curl of B, I can substitute equation 4. Okay. Then it's become minus t. Curl of B is just 1 over c squared e dt. Right? 1 over c squared e dt. So this becomes minus 1 over c squared t squared e, second derivative of electric field with respect to time. Okay. How about the left-hand side? The left-hand side is, take my word for it, or you probably learned this from math before, right? Curl of curl is a gradient of divergence. So this is E minus the Laplacian of E. Okay. Take my word for it, or go home, do your, it shouldn't be that difficult. Or just look at the math textbook, right? And that has to be equal to that, right? So you have, if I rearrange all the term, I have the Laplacians of E minus 1 over c squared, e squared, e squared. Okay. Same thing here. You can do this exercise at home, taking the curl of equation 4, right? You get the curl of B now, right? And that has to be equal to minus curl of, no minus in this case. Is that minus? Yeah, no minus. This is 1 over c squared. Change the order of the differentiation. Get 1 over c squared d curl of E, right? But the curl of E is no more than just minus d from equation 3, right? So this left-hand side, right-hand side, then this becomes minus 1 over c squared, e squared b. Right? Second derivative of d with respect to time. Same thing, this vector identity will give you minus the Laplacians of b. Okay? Because, I forgot one thing, right? Did I forget to mention it? The divergence of E is 0. That's the reason I think it is right this way. I somehow overlooked that part. Right? Because of the equation 1 and equation 2. Right? Okay. So same thing here. Since I mind a little bit there, let's just do it on this side. Okay. This term here on the left is just the gradient of the divergence of B minus the Laplacians of B. Right? But the divergence of B is 0. Right? This is from equation 2. Right? Okay. Now there's a lot of math here, unfortunately. So this is just because this drops, right? And you're left with the Laplacians of B with the minus sign. Right? So this will give you Laplacian of B minus 1 over c squared, b squared b dt squared. Is equal to 0. This is called a Maxwell equation. It's satisfied by both E and P. Okay? And this equation actually turns out this equation supports waves. Okay? So, in particular, just to be specific without lots of generality, consider a sinusoidal. It doesn't have to be this, right? But let's just consider a sinusoidal traveling wave. So, if you studied mechanics, did you do waves in mechanics in 7A?
A little bit.
Right? So you have a solution, a sine wave like that, that's traveling with some velocity in that direction. Okay, this is what I want to consider now. Right? Okay? So let's write, this is actually sine x minus b. Right? As you see, right, as you change x and t, you see that this whole pattern travels to the right. Okay? Let's consider an electric field. Let's write a different place. Let's consider an electric field given by, let's choose our coordinate system. Let's just, this is following yourself from here on. So this is x, y, and z. I'm considering wave traveling in the y direction. Okay? So let's consider E to be equal to E naught sine y minus t. Okay. So this part is the part that's traveling, right? This sine wave here. And of course the unit is strong. In reality, I have to have a constant in front of it, but I want to kill the constant for now because I don't want to carry it in all my differentiation, right? And I'll introduce the constant back afterwards. Right? Purcell did it that way too, so if Purcell does it that way, I'll do it that way also. And the B field is equal to not sine y minus t. Okay? And as you will see, if I take these two equations, right? Let's call this equation 5 and 6. Right? And maybe not. If I take these two electric field and magnetic field and substitute it into the Maxwell equation, right? 5 and 6, then what do I have? I have the Laplacians of E. Okay? That will just give me, if you look at this, this function only has a y dependence, right? So the Laplacians of E, recall Laplacian is the second derivative of x with respect to x plus second derivative with respect to y plus the second derivative with respect to z. It's the whole thing multiplying the electric field, right? But this term is 0 because the electric field only has a y dependence. Right? So this becomes just e squared y squared. Right? So this is actually just dy if you look at easy. So easy. No, I'm not defining the expression for now. Right? So this is the functional form of the wave. Okay. So there's no y. Okay. And if I look at the other term, the minus 1 over c squared term, e squared d squared, what do I get? I take the derivative of this with respect to time. I pull out 2 factor of minus v, minus v, right? I differentiate the sine with respect to time. I get cosine, and I differentiate cosine, I get sine back, right? With a minus sign, right? So there's another minus sign of sine y minus v. Right, with the O times the now. Okay. So adding these two equations together, right? Well, I didn't actually do this. There's a lot of algebra. If I differentiate the electric field with respect to y, right, then I get differentiate sine. I get cosine. I differentiate again. I get minus sign, so this becomes minus minus d naught sine y minus 1. So this is this part here, and this is the time dependent part. Okay, and then the sum of the two has to be equal to 0. Right? So therefore minus d naught sine y minus vt, right, at this 2, and this becomes plus, right? The 4 minus sign, it becomes plus v squared, there's a c squared here, over c squared sine y minus vt has to be equal to 0. Okay? And the sign drops. Right? What did I do? There is an E naught somewhere here. There's an E naught here, right? Okay, the E naught cancel. Right? So I have minus 1 plus v squared over c squared. That's equal to 0. Okay? Therefore, v is equal to plus c or equal to minus c. So the wave is traveling to the right, then it's plus c. And if the wave is traveling to the left, it's minus c. You can do the same thing. It turns out it's redundant. If you do the same thing, but make sure that you check, right? Substituting this equation. Let's call this equation number 7 and 8. You see there's a lot of equation. If you substitute equation 8 into the Helmholtz equation for magnetic field, you will also get a condition that phi is equal to plus c or minus c. So you learn nothing new, right? Except that wave satisfy this equation with the same relation. Okay. Just bear with me, we're almost there. An equation for now. So at least we know now the velocity is at the speed of light. Okay? But you cannot yet write on that t-shirt that you like, because it's not adjust. Where are we here? I'm confused myself. Okay. Yes. I got a piece of paper now. Anyway. So we're almost there, right? We just have to find the relationship between, we know that the wave is traveling in the y direction, right? We just have to find the relationship between the y direction and then E naught, and then we're done, right? Okay. So let's look at so to do that, let's take equation number, oh, I erased it. Anyway, let's look at the divergence of E. So in this case here, the only thing that matters is this is just dx plus dy plus dc, right? Okay. The electric field only has a functional dependence on y, right? Okay, right? So this is identity zero. Right? The only possible non-zero component is this. Maybe it's non-zero. Right? Okay. So in order to satisfy the equation that the divergence of E is zero, right? Dy has to be zero. Identity. Okay. So E has to be E naught can only point in the x, right? Okay. Recall. So the electric field actually has to be in this plane here. Right? It cannot be in the y direction. Right? This is very unlike a sound wave that you're familiar with from 7A, right? When you discuss wave, sound wave is actually a longitudinal wave. Right? So the amplitude is actually along the direction of motion. Right? This is a transverse wave. Right? As a result of this is a transverse wave. This is very low. Right? And this is more like the wave on a string, right? If you wiggle a string, right, then the amplitude is actually perpendicular to the direction of motion. Electric field wave is like that. Okay? So without loss of generality again, let's consider E naught be actually E naught in the C direction, right? So I look at a wave like this. Is that a sine wave? Yeah, I'm just sine. For some use cosine, but for some I use cosine. That doesn't matter. Except for so the electric field is like that. Along C direction. Okay. So what's the condition of B?
How do you know that it's in the z direction, not in the x direction?
Oh, I just happen to choose a particular linear polarization, say, just without loss of generality. I can also rotate my coordinate system. Right? I can rotate my Cartesian coordinate in such a way that the z direction is along the direction of E naught. Right? But in theory, I don't have to. In fact, it's more natural to talk about all this later on to use circular polarization instead. But for the purpose of this discussion, this is fine. Right? So E is along the z direction, so same thing. I look at the divergence of E, that has to be equal to 0. Right? Same argument, to make a long story short, B naught has to also be the x equivalent. Okay. But we don't know yet, right? We don't have, there is at this point E and B, they are decoupled, right? There is no coupling between A and B so far, right? Right. So where does the coupling come from? The coupling comes from the equation 3 and 4 of Maxwell equation, right? The induction part. This is where E couples to B, and E couples to E. Okay, so let's take a curl of E. What is a curl of E? Curl of E is spell it out, right? Is this thing here, right? It's a determinant of all this thing here. If you're not familiar with this, you should install your math book. Okay. So I only have EC here, right? This is 0. This is 0. Right? Okay? And the only dependence, the only functional dependence of the electric field is only with y. Right? So this will only give me one term. And that one term is actually along the z direction of DEC dy. Right? And that has to be equal to, if I do the math right, it's in the z direction, not cosine y minus e. Okay? It's the curve. And then the other term, if I look at the minus dT, what do I have? I have a B naught with a minus sign, right? Minus B naught. And keeping it as vector, right? And then I differentiate sine y minus vt with respect to time. I get a factor of minus v cosine y minus v. Okay? So this becomes minus B naught. C squared somewhere. Nope, everything is fine. This becomes plus, right? The minus cancel that minus. E cosine y minus e. Right? So let's compare these two equations, right? Because I'm just looking at this equation. Right? They have to be equal. Right? The cosine cancel. Right? This is also in the z direction, by the way. Or no, this is, I have no direction yet here. So I have P naught V is equal to E naught C. Okay? Therefore, P naught has to be, I'm making a mistake somewhere.
Shouldn't that be an X?
Yeah, there should be an X. Yes. This is an X. Okay. So this is an X here. Right? So B naught has to be in the X direction. Right? And in particular, since V is equal to plus or minus C, right, then V naught, Cp naught has to be equal to plus minus E naught. Okay. So just to spell it out, if the wave is traveling